Hello and welcome. Today we're going to be looking at conditional probabilities. So we want to be able to find conditional probabilities and be able to use tables and tree diagrams to help determine conditional probabilities. And we get to start by looking at or considering one of my all-time favorite probability questions. So this is kind of a classic math problem. We've got a great prize inside of either box 1, 2, or 3. And here's a possible scenario for how this could play out. So you choose box 1. And so then you are shown that box 2 contains a rubber chicken. So unless you're a real big fan of rubber chickens, not a great prize. You're given a chance to change your choice. So the idea is, should you stay with box 1 or should you change to box 3 in order to try to get the great prize? Now, I don't want to ruin the answer or puzzle for you by giving you the answer. Like I said, this is kind of a classic question. I will tell you that one way is better than another. So either switching or staying, they're not the same. So I'll give you that much of a hint. But kind of a classic problem. You may have actually even heard this one before. But a really good one to think about. And maybe after we do some work with conditional probabilities, you might have a little bit better chance of coming up with the correct response here. And of course, just coming up with the answer isn't okay, or not enough really. We want you to also be able to explain to someone else why your way is better. So again, good puzzle for you to try working on. So talking about conditional probability, we're looking at the probability that an event B will occur given that some other event A has already occurred. That's what we call a conditional probability. So there's that condition that we already know event A has happened. So what is the probability of event B given that event A has already happened? Conditional probability exists when two events are dependent. So meaning that their probabilities affect each other, or whether one has happened or not affects the probability of the other happening. Here is some notation for conditional probability. We write it this way, and we read it the probability of event B given event A. So there we're saying that we already know event A has happened. So what is the probability of event B given that event A has already happened? So as it says, tables and tree diagrams are going to be helpful finding conditional probabilities. We'll start with a table of information. So this table shows students by gender at 2- and 4-year colleges and graduate schools in 2005. And we're going to pick a student at random and try to figure out these different probabilities. So first of all, finding the probability that the student is female given that they are in graduate school. Now, even without necessarily considering the question, one thing that will be helpful here is to total up these different rows and columns. I might have to scoot this over a little bit to have enough room to total these up. So totaling up these rows and columns. So we'll go ahead and do that quick. Alright, so here we have our totals. So looking at the different rows and columns, total number of males, 7,539. And again, these numbers are in thousands, so really you could add 3 zeros. I'll just refer to them as they appear. Total number of females, 9,993. Number of students in 2-year colleges, 4,328. 4-year colleges, 9,841. Graduate schools, 3,303. And grand total, 17,472. And again, that's thousands, so really 17,472,000 for a grand total. So thinking of probably the student is female given that they are in graduate school. So what that does for us is that allows us just to focus on this single row. So the number of students in the graduate school, 3,303, would be the denominator. That's our sample space. And the numerator would be the number of females in graduate school, so 1,954. So again, if you can imagine having all of this information somewhere, and you pull up one piece of information, and the first thing that you notice is that it's someone who is in graduate school. Then we'd really be looking at, okay, now that we know that it's someone from graduate school, what's the probability that that person is female? And that's where we get the 1,954 over 3,303. And that probability turns out to be a little over 59%. So it's approximately, we'll call it 59.2%. Just so we have a kind of an idea of what that is. The next question is just what is the probability that the person is female? So no conditions. So that means we're looking at our entire sample. Again, we are still sampling from these universities or these students. So our denominator would be the entire sample space, the 17,472. And the numerator would be the number of females. So that would really be the 9,933. So out of all those universities, what's the probability that that student selected at random would be a female? So we've got our value there that we're going to figure out. And that turns out to be approximately 56.9%. And so that's what we're looking at for what's the probability that a student selected would be female. We've got a couple other questions based on this data. Next one we have is what is the probability that the student is attending a four-year school given that the student is male? So kind of flipping around the conditions. So now we're looking at the student has to be male. So our condition means that we're focusing on just this column of information. So our sample space would be the 7,539. So that would be our denominator. And then the chance that they're going to a four-year college is the 4,324 that we have. And that turns out to be about 57.4%. Next one we have actually asks us just to think about it. So without calculating, given that a student is enrolled in a four-year college, is it more likely that the student be male or female? So again, what's the given condition? Let's make sure you're clear there. So given that they're enrolled in a four-year college, well, also all we have to do is look at our four-year college. So that's this single row here. So there's 4,324 males, 5,517 females. So is it more likely that a student be male or female in that group? And so without calculating the percentages, since there are more females in that group, they'd be over 50% chance, whereas males would be less than 50% chance. Here's a similar setup for this one. This one's talking about municipal waste collected, and again, this is millions of tons, but I'll generally just refer to these numbers as they appear. So in this problem it says Americans recycle increasing amounts through municipal waste collection. Table shows collection data for 2007. What is the probability that a sample of recycled waste is paper? So again, they don't, they just kind of write out the question. They don't give us what it looks like using that conditional probability notation. So that's where we have to then consider what is the condition. Well, so again, the probability of the sample of recycled waste is paper. So they're telling us the condition that it's recycled. So we are looking at just that column, and then the question is, well, what's the chance that if it's recycled that it's paper? Again, we'll want to have the totals for those different rows and columns, so I'll go ahead and I'll fill those in. Alright, so now we have those values, and like I mentioned, again, looking at that recycled column. So the recycled column has a total of 79.4, so that's our denominator. And the chance that that's paper would be a 45.2, because there's that 45.2 million tons of recycled paper out of the 79.4 million tons of recycled waste altogether. And this turns out to be roughly 56.9%. Next question we'll take a look at. What is the probability that a sample of recycled waste is plastic? So again, we're still looking at recycled waste, so we'd have the same denominator, 79.4. So a denominator of 79.4. Numerator, recycled plastic, would be 2.1. And so then we get our fraction, we can approximate that. And that turns out to be only about 2.6%. Then one final question for this data. What is the probability that a sample of recycled waste is glass? So again, still looking at recycled waste, so our denominator remains the 79.4 for that total. And then glass is 3.2 million tons. And this turns out to be just over 4%, so I'm going to call it 4.0% just so it's clear how much I rounded that. So in this case, based on the questions that they ask, I did find a lot of numbers that I did not end up using. However, sometimes that might just be, easier than waiting to see and finding out, just those numbers that you need. Although in this case, maybe it wouldn't have been so bad just knowing that the condition was always recycled waste. So, all right, next we've got a formula for conditional probability. And so with this formula, we have really for two events, A and B, that as long as the probability of A does not equal 0, then we can use this in order to calculate it, the probability of B given that event A has already happened. Now in this case, the formula is solved for the conditional probability of B given A. However, you could solve it for either the probability of A or the probability of A and B. So either way, or really three ways that you could have this solved for. The text gets into this a little bit later, so I'll just go into this now so we get it on this slide here. One of the simple things to do would be to multiply both sides of this equation by the probability of A. What will happen there is if I have a probability of A here, then those would cancel, and over here I'd have the probability of A times the probability of B given A. So that's what the probability of A and B would equal. Would equal the probability of event A multiplied by the probability of event B given that event A has already happened. So that's one additional way we could have that solved for, the probability of A and B. So the third and final way that we could solve this would be to solve it for the probability of A. Well, so we'd actually start with what we did here, multiply both sides by the probability of A, but then divide both sides by the probability of B given A. That will isolate the probability of A. So if I have the probability of A all by itself, again that happened because I would have to divide both sides by the probability of B given A. So probability of A and B would get divided by the probability of B given A. So a couple different, or really three different ways to have that solved. And again, you really only need the one way, and then everyone should be able to use algebra in order to solve that for any of those three different pieces. But so three ways we can use that conditional probability formula. Now, in these cases, when we have a table of information, yes, we could just use that table in order to figure out our conditional probabilities. But again, we're trying to prepare for a situation where maybe we don't have all of the information and only have certain pieces. So even though we have the tables, we're going to kind of pretend that we don't and practice using our formulas. So in this first question here, we've got a utility company asked 50 of its customers whether they pay their bills online or by mail. What is the probability that a customer pays the bill online given that the customer is male? So you can see here our formula, and then here we translate our different A's and B's. So B is that the bill is paid online, A is that the person paying the bill is a male, and so then A and B end up on top, so probability of male and online. divided by the probability of, again, that conditional statement, so the probability that they are male. So again, really we find these two probabilities. That's what we have here. Probability that the person is male and they pay their bill online is 12, male and online. So that's where that comes from. Again, it's that kind of intersection of those two events. And then the total is 50. And we could get that a couple of different ways. Again, if we filled in the rest of that information on the table. But again, we're trying to pretend as if maybe we just knew the probability of male and online was 12 out of 50 rather than just having the entire table. But again, if you were to add those together, you get 20 male respondents, 30 female respondents for a total of 50. That's where the 50 comes from. And then our denominator is just the probability of the customer being male. Well, so there's 20 males altogether. So again, just male, 12 and 8 makes 20. And then 50 customers altogether. So 50, 20 over 50. So then what we end up with is our conditional probability. We get 12 over 50 divided by 20 over 50. And notice what I did there is I wrote that fraction as a division problem. Of course, what we want to do then is change the division to multiplying by the reciprocal, and you'll see how that works out to cancel out those 50s, and we get 12 out of 20, which of course reduces down, and I'm sure you can see there that the greatest common factor for 12 and 20 would be 4, and so we end up with 3/5 or 60% chance that the person pays their bill online given that they're male. So 3 out of 5 or 60% chance. And again, like I said a few times now, we could have figured this out just from the table, but we want to practice using our formulas a little bit. Here's another one. I find this question to be entertaining. Researchers asked shampoo users whether they apply shampoo directly to the head or indirectly using a hand. And then the question they ask is, what is the probability that a respondent applies shampoo directly to the head given that the respondent is female? And this would be a good chance also for you to just pause and try the problem on your own, and then resume the video and I'll work through it the rest of the way. Alright, so assuming you've had a chance to take a look at this on your own then, again I kind of underlined the given condition. So really the question we're looking at, if we translate it, would be what's the probability that the shampoo is applied directly to the head given that the respondent is female. And so then we can translate to our formula. So we have in our numerator then would be female and directly. I'm going to abbreviate a little bit here. So F and D, female and directly. And then in the denominator, one way that I find that is easier to remember this is to remember that it's the given condition that goes in the denominator. So female and directly divided by female is what we would be looking at. So if we figure out those two probabilities, again, totals might be nice, although now that I'm looking at it, these numbers, I guess they're a little bit different. We got 2 and 18 and 6 and 24, whereas we had 12 and 8 before. So kind of close. Alright, so let's see. We need female and directly. So what we're looking at here is the only place that satisfies that condition is right here. So that's our 6. And the total number of respondents would be 50, because 30 female, 20 male, that makes 50 respondents. So probably a female and directly is 6 out of 50. Now, of course, I realize that would reduce, but I want to just hold off for a second. And so I'll divide by the probability that the respondent is female. So again, I'm going to actually write this as a division question. So probably the respondent is female, or there's 30 females. out of 50 total respondents. So again, I want to write that as a division problem because then I can multiply by the reciprocal. So 50 over 30, the 50s cancel. We're left with 6 out of 30, which is a total of, let's put it over here, 1/5. So you get 1/5 or 20% chance that the respondent applies the shampoo directly to their head, given that the respondent is female. Here's another good problem for you to work on your own. Again, given the table, I would probably just use that for the most part, although you could, again, use those formulas. So again, if you want to go ahead and pause the video, and then I'll work through these, and you can check to see if you came up with the same values. So probably the person, so again, really what we're looking at here, table shows number of male and female students in a certain classroom who take notes using different methods. So it's probability they take notes on their laptop, given that the respondent is male. So laptop is 27, male is 71. So 27 over 71 is what you should be coming up with. And approximating that as a percentage would be appropriate in this case. So that turns out to be about 38.0%. And again, the zero is important. It shows that I rounded to the nearest tenth of a percent. Next one, probably the student is female, given that they use a voice recorder. Well, so the given condition of the voice recorder means that we're only looking at this row here. So there's 3 total students, one of which is female. So 1 out of 3 for 33.3 repeating percent. Next one, what is the probability that they use pencil and paper? So now notice again there's no condition here. So pencil and paper is a total of 70, and then the entire sample was 133. And so we would again want to approximate that. And that turns out to be about 52.6%. And then the final one, what is the probability that the student is male, given that they use pencil and paper? So again, the pencil paper condition means that we're looking at just this row. So total there is 70. So that's our denominator. And males there would be 42. And again, remember, I'm kind of taking the easy way here, not using the formulas. Again, you want to practice because we will have some questions where you have to know how to put that together. This does turn out to be exactly 60%. All right, here we get to our last slide, and I mentioned earlier, again, using this formula in different ways. So here's the one that they mention is using the formula if it's solved for the probability of A and B. So probability of A and B equals probability of A times the probability of B given A. So again, we'll use that along with 3 diagrams to help find probabilities of dependent events. So we have a school system compiled the following information from a survey it sent to people who were juniors 10 years earlier. So it says 85% of the students graduated from high school. So we create a tree diagram, and so trying to do this in the space that I have here. Tree diagram would branch off like this. So we've got our entire sample space here, and we have an 85% chance that they graduated. So I'll put G for graduated. And so they don't necessarily say this, but that would mean that there's a 15% chance that they did not graduate. It says then that of the students who graduated from high school, 90% are happy with their present jobs. So we would get a second branch, and so we would have happy here, and that's 90% of the students that graduated from high school are happy. And then we'd have not happy here, and so that would be 10% that graduated from school that would not be happy. The third point they offer is that of the students who did not graduate from high school, 60% are happy with their present jobs. So again, we'd have another branch here. So if I put not happy here and happy here, so 60% chance that they are happy, so that would mean 40% chance that they're not happy with their present job. So that's what our tree diagram looks like. And their question is, what is the probability that a person from the junior class 10 years ago graduated from high school and is happy with his or her present job? So again, they have their formula. If I can scroll back up here. Probability of A and B equals the probability of A times the probability of B given A. So again, probability of A and B equals the probability of A multiplied by the probability of B given A. So that's our formula. Now if we translate that to what we are trying to find, so trying to find the probability that they graduated from high school and they're happy with their present job. So really in my shorthand that would be G and H. So graduated and happy. So again, really what we're looking at then, we take the probability that they graduated, multiply that by the probability that they're happy given that they graduated. So we can figure out those two probabilities. So we know the probability that they graduated was 85%. So probability that they graduated was 85%. So we know what that is. Now this conditional probability that they're happy given that they graduated is really this percentage here. Probability that they're happy given that they graduated. So again, this probability here is conditional on the fact that we know that they graduated. And so we know that that would be 90%. So we'd multiply 85% by 90%. I'm just going to put the 0 there to help everybody see that that's really 90%. And so we end up with, and again that's really our probability, they graduated and they're happy. So that turns out to be 76.5%, and that's exact, not rounded at all. And so that's how we can do that using the formula. And when we have the tree diagram, we can actually maybe do that a little bit easier without even using the formulas, and I'll kind of talk about that a little bit here as well. The next question they have is, what is the probability the student from the junior class 10 years ago in problem 4 did not graduate and is happy with his or her present job? So really what we're looking at then here, so again I'll just kind of talk my way through the diagram, is look at what path we're going down. So did not graduate, so we're going this direction, and is happy, so then goes down this way. So did not graduate and is happy looks like that. So really to find that probability is we just multiply those two probabilities together. So 15% times 60% is what we'd be looking at. And that turns out to be a grand total of 9%. So again, that's 15% or 0.15 times 0.6. Again, you can put the 0 here if you want to emphasize that that's a 60. Make that 6 look a little bit better. And that turns out to be 9%. Alright, well thank you for watching, and of course remember this, especially with newer material, if you have questions, do not be afraid to ask and get some help. But yeah, thanks for watching, and best of luck with this material.